Thank you very much for the invitation, and I want to thank the organizers for allowing me to participate in this celebration of Sergio and his work. It's really an honor. So I guess, Sergio, we met in 2012 when I was a first-year assistant professor in Princeton, and you taught a graduate class on PDEs. And I remember in the first lecture you came in, and you said, well, there really is just one important nonlinear PDE, the Einstein vacuum equations. And then you looked at me and you said, okay, fine, the Euler equations are okay. So here I am. Here I am.
You exaggerate.
Okay, so when in Rome, I cannot read French, but these are the Euler equations. You see acceleration per unit mass. Sorry, force per unit mass is acceleration. U, V, and W are the three components of velocity. Q is density, P is pressure. Supplemented with conservation of mass. And you can see that the guy who wrote this is a bit confused because he calls the pressure elasticity. And he's basically not happy because this model is not closed yet. Okay? And of course it's natural because Euler didn't know, the ideal gas law was not invented yet. He only knew this Boyle's law, that the volume of a given mass is inversely proportional to its pressure at constant temperature. And this is why he wants more equations. He basically wants a temperature equation. Can you see the typo in the Mémoire de l'Académie des Sciences? This G is a Q. That G is a Q. That's the typo. It's pretty cool that in 1757 you can actually read the math. Okay. So now we do know the ideal gas law, so I can write a full closed system. And it's just a compressible Euler equations. They were presented a few times already in the conference, in several talks. And I guess
a lot shorter in any case.
Sorry?
A lot shorter.
Yeah.
Einstein equations is still shorter.
Much shorter. So you have conservation of mass, momentum, and energy. You notice there's a pressure and an energy. They are related by the kinetic plus potential energy is total energy. And then the ideal gas law specifies the pressure as it relates to what is called specific entropy S. So you have the 1 over gamma rho to the gamma. By the way, I've set all constants to 1, the temperature and so on. And this is the exponential of the specific entropy. So now this is a closed system, and previously in the conference, this equation appeared actually with S being a constant. And for some of the things, for about 60% of the things that I will talk about today, it is very important that S is not a constant, that you actually do consider the full Euler equations. Okay, so this is just an equation. You need to supplement it with boundary conditions and initial conditions. I will not worry about boundaries, so it's either posed on the whole space or in a periodic box. And I always want to study the Cauchy problem with smooth data. And what I'm interested in is how this smooth data evolves, and then what happens once the smooth evolution stops. And because I'm interested in the evolution up to this time of the singularity, I'm allowed to rewrite the Euler equations because the solutions are smooth on the time interval I'm interested in. And one convenient way to rewrite them there are many convenient ways, sorry. But it's very convenient to reduce the speed of sound, the local speed of sound. It was presented before in the conference again, but it was presented with S is equal to 0. So this is just a derivative of the pressure with respect to density. It's a power law, and then e to the S on 2. If you ever see me write this alpha, it's just a different way of writing the adiabatic exponent. So normally people write adiabatic exponent as gamma. Gamma is bigger than 1, so gamma minus 1 is positive. So this alpha is positive for me. And basically you can write down an evolution, which is sometimes called the transport form, in which you evolve velocity, rescaled speed of sound. Speed of sound is okay, but this is even better. And entropy. And you see you have transport equations here, and then you have reaction terms. The reason for introducing sigma is that if the entropy is 0, these two terms look very, very symmetric. It's already symmetrized. You don't have to look at symmetrizers anymore. It's symmetrized. Okay. So typically, the standard singularity that forms is a shock. And we could have many interesting talks about shocks, and this is not what this talk is about. This talk is about what are called implosion singularities. So at the shock singularity, what happens is that the fundamental fields, velocity, density, pressure, they remain bounded, but certain gradients of them blow up. And I say certain gradients because the divergence blows up, but the curl does not. In fact, many times the equations are considered in the irrotational setting when the curl is actually 0. In an implosion singularity, the fundamental fields themselves blow up. Okay, the gradients also do, but the fundamental fields blow up. And notice I'm not saying which, and that's because that's a complicated story. So the first implosion singularity that was ever written down was by Guderley in 1942. And what he noticed is that if you basically go to self-similar coordinates, you can reduce the PDE to an ODE. ODE happened to be autonomous, so that was a beautiful reduction. And then we have theory for dealing with autonomous ODEs, at least up to some point. So here's what he was looking at. He was looking at the implosion of a gas in which, so the initial state, there's a spherical shock. Something created a massive shock. Okay, so gas is here. And something created a massive shock at radius 1. It's in spherical symmetry. And inside, it's quiescent. Nothing happens. Okay, so pressure 0, inside is 0. Velocity inside is 0. Density inside is whatever, 1. Oh, I wrote speed of sound instead of pressure. They're equivalent. Okay, pressure 0 and speed of sound being 0 are equivalent. And then basically Guderley says, okay, if this shock were to implode symmetrically, so to preserve spherical symmetry and will go inward, all I need to do is solve for the Euler equation in the exterior. And that's exactly what he did. So let me just go a little bit through his derivation. So he introduced a self-similar variable. I guess these days we are kind of used to this kind of transformations, but I want to say that by this time, there were very few papers on self-similar solutions before. Okay, so Taylor, von Neumann, and Sedov had written one before, and that's it. This was also the first time ever somebody... Sorry?
Riemann.
Was it self-similar?
Yeah, yes. I mean, the Riemann problem is in self-similar coordinates.
X over T.
Okay.
Okay. Okay. So that's what Guderley writes. And this lambda is a similarity exponent. And the remarkable thing about his paper is that as opposed to Taylor, von Neumann, and Sedov, you cannot determine lambda based on scaling or energetic arguments. So then he introduced, once he has the self-similar space variable, he introduced a self-similar velocity, self-similar speed of sound, and self-similar density. And I want to just look at how it looks like. Okay, so this is spherically symmetric, so it only points in the ER direction. There's a power law of time here, and then some function just of the self-similar space variable. Same for speed of sound, except for this, because it's a scalar, right? So you don't need any vectorial part. And the only thing that makes for the density is that it's minus t to power 0. So the initial data is prescribed at time -1, and the singularity is expected to happen at time 0. Notice that a posteriori, we're going to see that this exponent is bigger than 1. So in particular, this number is negative. So because it's negative, as t approaches 0, velocity blows up. Same for speed of sound, but not for density. Okay, the density does not blow up in Guderley's solution. Because he has gone to this self-similar coordinate, the location of the shock, which was before this power law, is now frozen. It's frozen at xc is equal to 1. And because he already knows the speed of the shock, and he knows the state inside, he can use Rankine-Huguenot to compute traces on the boundary from the outside. So there's enough information in the problem to have a well-posed problem. So now you're trying to solve for these profiles, V, Q, and D, and you have boundary condition for them at xc is equal to 1, and you want to solve this problem from xc is equal to 1 to xc is equal to infinity. That's the problem. And as I said earlier, it reduces to an ODE, and you can basically eliminate the entropy through a clever change of coordinates, and the ODEs look like this. This delta represents the product of the three wave speeds present in the system. So in compressible Euler equations, you have three important wave speeds. You have fluid velocity, which transports entropy and vorticity. And then you have fast acoustics, which is velocity plus speed of sound, and slow acoustics, which is velocity minus speed of sound. And the product of those three things is delta, okay? And then you have xc dxc, and then this is a quartic polynomial in those two letters with explicit coefficients. Now, because this is the same delta in both, you can just divide and you get an autonomous ODE. And that's it, okay? So that's what Guderley did. And of course, you solve autonomous ODEs by phase diagrams. So I've not plotted the entire phase diagram here. I have only plotted the piece that's relevant for Guderley, okay? This blue dot is the piece that corresponds to the boundary condition due to the Rankine-Huguenot condition, xc is equal to 1. This pink dot corresponds to xc is equal to infinity, where you want all fields to decay to 0. And then there's three curves. And these are the zero level sets of the important quantities appearing here, delta, PV, and PQ. And you notice they all intersect at this point. By the way, there's another one. This is a triple point, and so the unique smooth trajectory must pass from blue to pink through the triple point. There's no other way while retaining smoothness. And he, of course, cannot actually do this rigorously. He does it numerically. And this only works if lambda is chosen suitably. So the condition that you cross this point smoothly is determines lambda. It's the zero of some very complicated object, okay? To my surprise, the first rigorous proof of the existence of the Guderley profiles and their smoothness appeared in 2025. I don't know, I think it's just because nobody really cared.
Does it depend on the degree of smoothness?
No.
So it's C infinity?
It's C infinity. It's analytic, actually. This is how they look like, okay? So what I'm plotting here is the Guderley profiles in 3 dimensions for oxygen, diatomic gas. Diatomic gas corresponds to gamma is 7/5. And I'm gonna try to plot as if it's 2-dimensional, because I cannot plot 3 dimensions and then something. So I'm plotting 2 dimensions and something, but the object I computed is a 3-dimensional object. And you see that the shock wave goes inward. You see that the density here is capped by its value at the boundary of the circle. But the radial velocity goes to negative infinity, and the pressure is going to jump to positive infinity, okay? And that's exactly what it's supposed to do. And they're smooth and so on. Okay, so in the physics community, my understanding is that it is well understood that this does not describe an imploding shock at the time of the implosion. And neither does anybody know where the shock came from. Because how do you generate that huge shock in the first place, okay? Okay, you put some dynamite and you explode it, but okay. So, however, physicists say that at intermediary times, it does describe properly how a spherically imploding shock goes in. At the time of the implosion, physics doesn't make sense anymore. Velocity goes to negative infinity, although speed of light is finite. Pressure goes to infinity, but density remaining bounded, that's just a misnomer, because molecules have finite diameter. So if you squeeze them, but the density just remains bounded, and you squeeze them in a unit volume, it becomes a stiff gas. It becomes incompressible. So at some point, it cannot go inward anymore. So anyway, that's fine. It was not meant to do that. Numerically, my understanding is that the complication with Guderley is that it's quite expensive to calculate the similarity exponent. And if you miss a little bit, it kind of misses your computations. And this is the worst of all issues with Guderley. It is assumed that the pressure inside is zero, the zero function. Now, when you numerically simulate this, you're going to put some kind of regularization, like viscosity. Viscosity is instantly going to lift the pressure. It's not going to be zero anymore. And it's a well-known issue in the numerics community that you cannot retain zero pressure in an open set. What I wanted to know is, where is this huge shock coming from? If you read Landau's book, it's coming from infinity. Okay, fine. And what I was interested in is whether this is a solution of a Cauchy problem. And if so, is it a Cauchy problem with smooth data? Because I don't want to take that data, okay? And the answer is, well, yes. So that's a theorem with Giorgio Cialdea and Steve Shkoller. So you fix dimension, fix adiabatic exponent, and you fix what is called the matching time. So let me draw a picture here in which I have time. Here I have space. The implosion is going to happen at time 0. Initial data is prescribed at some initial time, and there's some matching time, TF, T-fin. There exist infinitely many classical initial data. You saw in the first talk of this morning that by classical it's meant C1. They're smoother than that. Okay. I will give very precise meaning. Specified at some initial time. The data is radially symmetric, of course. Inside of the core region here, it represents fluid at rest or gas at rest. It is globally C2. In fact, it's piecewise C infinity, but okay. And it has two very special radii across which it's exactly C1 1/3. Okay? And with this infinitely many initial data, what you can do is the following. Screw this. Okay, so you can evolve this data forward. It's classical, so there's a unique evolution. There's no shocks, you know. And then at some time, T star, there's a unique point R where a pre-shock forms. What does that mean? The gradient of the solution has blown up, but there's no true shock yet. There's no jump discontinuity. It's just Hölder continuous, okay? And there's a unique label, a radius, R star, at which this happens. And it only happens for what is called the dominant Riemann variable, which is velocity minus speed of sound. This is the fast acoustic, because velocity is negative, because it points inward. So if you have a negative velocity and you subtract speed of sound, that's the dominant object. After that, what do you expect to happen? Well, you expect instantly a shock to happen, a true shock, okay? And that's indeed what's going to happen, but it's going to be very small. It's going to be a small shock. In the weak shock, you're going to be in the weak shock regime. And the people who have worked maybe in this audience on the Czech development problem know that our current technology for studying the shock development problem allows you to prove that a small shock forms. And that's it. It is open, it's an open problem. How do you prove that this shock keeps growing and you get an order 1 shock, needless to say a huge shock? Okay, that is not known. And yet this does happen. Okay, so instantaneously from this R star, a shock current forms. On either side of the shock, so take a time slice. This is a classical shock. On either side, you're C infinity. Although you have only started as C1 1/3. The shock evolves according to RH. And moreover, at this... yeah. When Giorgio told me, I was like, that's impossible. It's possible. And then at time t fin, you are Guderley. You're not in the vicinity of Guderley, you are Guderley. Okay? So at this time, you have become the Guderley solution, which implodes and then explodes. Okay? And for all later times, you are C infinity on either side of the shock. It's global in time with one shock. As opposed to Landau's two shock solutions, these are one shock solutions, which are global in time. Okay, so this is the proof by picture, which is kind of there. So what we did is we actually solved it backwards in time. Okay, and okay, if you solve Euler equation backwards in time, that's perfectly fine as long as the solutions are smooth. But if you have shock, you have some entropy. Entropy dissipates information. So you should not be allowed to go backwards in time. Because backwards in time, you should gain information. I mean, where from, right? Yet you can do it. So what we do is, okay, here you are Guderley. And then we design a shock curve, which is carefully designed through a complicated iteration, such that at this time t star, you have no more jumps, but instead you have a 1/3 cusp. Now, because you have solved backwards in time and Guderley was smooth, you preserve smoothness. But now comes the issue, if from this cusp you now want to become, from Hölder continuous, you want to become C1 alpha, you need to gain regularity backwards in time. Okay? And that does happen. However, the fast and the slow acoustic carry with them information from this pre-shock, and they cause these two labels when you are C1 1/3. And you cannot be smoother. So that's a theorem you can prove. If you want to be C2 here, it is impossible that you're going to be C infinity, C infinity. It is crucial that if you want to be smooth at later times, that you build in some singularities here which collide, cancel each other out, and completely vanish forward in time. Otherwise, this is just impossible. Okay, so that's the first result. My understanding is that this is the first time ever where you can actually build a large shock. Now, so we were in 1942, then we're jumping to 2022, where there was this, I don't know, amazing paper of Mera, Raphael, Rodniansky, and Seftel, in which they discovered what is called a smooth implosion, an implosion which does not have a shock. And I don't know, I think nobody expected these objects to exist, and yet they do. So I will, because these are long names, I will refer to the paper by the acronym. So the theorem is that in 2 and 3 dimensions, and higher actually, sorry. I only wrote 2 and 3 because I care about fluids, but it works in higher dimensions as well. For all adiabatic exponents except a potential exceptional set, there exists not just one similarity exponent, but an entire discrete sequence of blow-up speeds which accumulate somewhere. And for each one of these exponents, lambda n, you can find C infinity smooth, radially symmetric, smooth implosion profiles. And moreover, you can prove that within spherical symmetry, these profiles are stable modulo a finite codimensional subspace that you unfortunately can't really quantify. Now, the beginning of the proof is the same as Guderley. You write the same ansatz, you get the same ODE. However, as opposed to Guderley, now you don't just want to cross the triple point from one point to another, you must have a global solution that extends to infinity. And that is exceptionally hard. So somehow they did it. Okay. Now, there were some follow-ups after this paper. I guess one of the motivations for the follow-ups is that the Guderley or MRSS phase diagram degenerates in the case of a monoatomic gas some points they collide. And so Buckmaster, Caolabora, and Gomez-Serrano, they did a very similar proof, but they were able to extend the construction and prove the same result, but for all adiabatic exponents. Okay? And it will become apparent a bit later why I'm going to mention this third result of Shao, Weng, Wei, and Zhang, who have revisited this specific adiabatic exponent of a monoatomic gas in 3 dimensions. And they proved, again, that you have a countable sequence of blow-up speeds for this one adiabatic exponent. According with them, you get a countable sequence of C-infinity smooth implosion profiles. And they accumulated a specific number, which is 3 minus root 3. Okay, it's bigger than 1. Oh, it's 127. And this is the largest known self-similar exponent, what I wrote there. Okay, so this will play a role a bit later. So the second part of the talk was, what are implosions good for? And when you ask that question, you need to also ask, good for who? Applied mathematicians that I've talked to, they don't really care about smooth implosions because they really say, okay, a shock forms, okay. I have never seen on my computer a smooth implosion. Experiments don't have that, so they don't really care. But mathematicians, on the other hand, went to town, and I guess I'm one of them. And you can prove very interesting results once you have these smooth implosions. And of course, the first were Merrill, Rodniansky, Raphael, and Seftel, who proved that you can use the smooth Euler implosions to prove blow-up of barotropic Navier-Stokes. So that's when you entropy or temperature doesn't appear, with linear viscosity, so the viscosity is a constant. And this result was then replicated. By the way, this result is false without linear viscosity. If the viscosity depends on density, let's say linearly or something that grows, at the implosion, the density makes the viscosity becomes huge and it arrests the implosion. I think somebody should just prove that. It's not that hard. Then they had this other amazing result about energy supercritical defocusing in LS. And then other people extended it to relativistic Euler with isothermal equation of state and complex wave equations. Again, there were many other things. So I come from an incompressible world. For me, this is still a bit a strange universe. And the incompressible world that I come from, vorticity is the only thing that matters. And of course, these are spherically symmetric, they're irrotational, right? So I was always curious, what happens to vorticity in 2D Euler? And what we do know is that at a shock, it remains finite. Okay, you can just prove that. When you have a classical shock, the vorticity remains finite. And moreover, you have very strong rigidity for the vorticity. In 2 dimensions, it's transported. Okay, if you divide it by density, this is the so-called specific vorticity. Vorticity divided by density, it's just obeys a transport equation. So in particular, if capital X are the characteristics of U, you just compose this with characteristics and you get that the vorticity at this location is the density at that location times the vorticity at the label it came from divided by the density at the label it came from. So if you just look at this, you say, but look, an implosion density blows up, hence vorticity blows up, right? But of course, it doesn't work like that. Why? Because the initial data is irrotational, so vorticity is 0. But it's actually a bit more tricky. So a very nice paper of Caolabora, Gomez-Serrano, Xi, and Stafilani proved that the smooth implosions are actually not just stable modulo finite codimension in spherical symmetry, but even outside of spherical symmetry. Okay? So you can perturb modulo an unknown finite codimension outside of spherical symmetry. So you've now solved this problem that you can choose initial data without 0 vorticity. The problem is that this modulo of finite dimensional space is unquantifiable. So you do not know that that constraint by accident doesn't tell you, okay, so this initial label A star gets carried by the flow to the implosion. You cannot rule out that the vorticity isn't 0 exactly at that label, simply because you don't know what this finite dimensional subspace is. Moreover, it's somehow contradictory, right? When you want to prove blow up of a PDE, you go to self-similar to discover that there's a profile, right? But the profile for vorticity is 0. Okay, so then you know, based on other equations, that you need to look at the next order. And that's what we did. Okay, so the theorem with my former postdoc Gia Chen, my student Giorgio, and my longtime collaborator Steve Shkoller from last year says that you take 2 dimensions. Why 2 dimensions? Because that's the hardest case. In 2 dimensions, vorticity has the most constraints on it. There exists initial velocity of compact support, initial sound speed or pressure, which is smooth and bounded from below, such that the 2D isentropic Euler system blows up at time t star. And okay, velocity, radial velocity blows up and it goes in self-similar land to a profile. Angular velocity, well, it goes to 0 in this coordinates, right? Because the profile is 0 for angular velocity. Speed of sound goes to the profile. And vorticity blows up, but you see the rate of blow up is slower than for velocity or speed of sound. It's at the next order. Okay, so this implosion, which was non-radial, basically we had to work very hard to make it non-radial. We made it axisymmetric. And what we were able to prove is that as in this coordinate, you have the radial implosion happening, still modulo finite codimension. In the swirl direction, you can prove full stability. There's no finite codimension. It's just stable, end of story. So that means you just perturb it, and that's it. So that's the proof. You prove that in the angular direction, you have full stability. Okay, so we were happy with this. So now I will switch topics, and I will tell you a little bit about the Landau equation. So the Landau equation was derived famously by Landau to model weakly coupled charged particles with Coulomb collisions in a plasma. And it's an alternative or a simplification to Boltzmann. Actually, in this grazing limit, it's actually the replacement of Boltzmann. Okay, so like all good kinetic equations, you can write them as dtf plus v grad xf is qff. Q is a collision operator which only acts on velocities, does not act on t and x. F is a function of t, x, and v. It's a probability density. And the collision kernel is explicit. Okay, it's the divergence of some coefficient grad minus the second function divergence of some coefficient. Who's that coefficient? You take your density and you get a matrix out of it by the following procedure. You convolve with a potential in the direction orthogonal to v. Okay? And as I said earlier, the only physically meaningful case is gamma is -3. If you want other gammas, you need to go to Boltzmann. In Boltzmann, yes, many parameters are physically relevant. In Landau, only one is, and this then corresponds to the Newtonian potential. It's 1 over v. Convolving with 1 over v, that's the Newtonian potential. However, that doesn't stop mathematicians to consider other gammas. The other thing I want to say is that this is a nice collision operator such that it has hydrodynamic quantities, a Maxwellian supported on hydrodynamic quantities, which you compute by taking moments of your probability distribution, and you get density, mass, and energy. Okay. So now let's do a little computation. So the next slide is going to be a bit painful, I'm sorry. No, not this slide, the next one. This one's easy. It just says that if you start with homogeneous data, meaning and nice homogeneous data, which is V dependent, then the solution remains homogeneous, only V dependent. And Villani in 98 proved global well-posedness for gamma is equal to 0. Of course, his proof actually is more general. And in a subsequent paper with de Villette, they proved the same result for actually, they write that it's gamma between 0 and 2, but I'm pretty sure, Jonathan, that it works for all gamma. You can go to infinity if you want. But they write it for 0 and 2. Wu, and then independently and later Silvestre, then started to take gamma negative. They got what are so-called moderately soft potentials. And then last year there was a huge breakthrough by Guillen and Silvestre, who proved the monotonicity of the Fisher information, and as a consequence, global existence for the Coulomb case. So these are, in the homogeneous case, what's known. In the inhomogeneous case, very little is known. There's a famous and very influential paper of Yang Guo, who proved that small perturbations of a global Maxwellian remain small perturbations of a global Maxwellian, and they go back to it. And there's a more recent paper of Jonathan, who perturbs not the Maxwellian, but vacuum, which is a degenerate steady state. And it's again, Jonathan, I think you have moderately soft potentials, and then Sanchit has hard potentials. And that's really all what's known. Okay, so this is the technical slide, the next one. Okay, so the question is, are there Euler implosions hidden in the Landau equation? Okay, so let's say you start to try to find them. So you make a self-similar ansatz, and you have 3 objects to make a self-similar ansatz for the field itself. So that's why there's CF. It's a similarity exponent for F, a similarity exponent for X, and a similarity exponent for V. You go to log time, let's not worry for a moment about modulation of time. You plug this into Landau. Now, because you need to balance dt and v dot grad, you automatically get this relation. It's built in. So you have 2 free parameters, CV and CF. Cx is actually determined. And when you plug it into Landau, because the Landau collision operator only acts on V and it's scaling invariant, it just goes through. But you get in front a power that depends on time, on self-similar time. So this is the old Landau equation, transport equals collision, and then you have 3 new terms coming from self-similarity. Now this 1 over epsilon s, as the name suggests, epsilon is meant to be small. But it was not small initially, it was 1, right? So the only way that it's small is if this exponent here is a negative number, so that when you send s to infinity, it becomes small. That's the only way it will ever be small. So the question is it possible that you get a negative number there? If you could, then what you have discovered is that although you have started with a Landau equation at unit Knudsen number, in self-similar coordinates asymptotically towards the blow-up, you have a hydrodynamic limit that all of a sudden emerged out of nothing. And we know more about hydrodynamic limits. So what you expect, of course, is that you converge to a Maxwellian, because you need Q F. If you converge to something, let's call it F bar, then that F bar better be a Maxwellian, because it needs to annihilate the collision kernel. Now, the Landau equation, you just take its moments and you discover that F bar has to be not just a Maxwellian, but a Maxwellian built on an Euler solution in 3 dimensions for a monoatomic gas, right? That's why that's 3 halves there. And so capital U, capital theta, and rho are the density, velocity, and temperature corresponding to 3D compressible Euler with this adiabatic exponent in 3D. And this is what you must have. Now notice this is not a global Maxwellian, it's a local Maxwellian. It depends on X. A priori, it also depends on time, by the way, a priori. Although, obviously, it shouldn't. Okay, so you kind of, I just repeated what I said, that you just take moments and you discover who the dihydrodynamic quantities are. So now the talk started with Euler, so let's go back to Euler. So you plug in to Landau, you just make some small definitions. You just define entropy as this power of density times temperature. You define speed of sound as this power of density times e to the root entropy. Okay, and the Landau equation becomes this system. And of course, these are the compressible Euler equations. Okay, so now the next question you ask yourself is, okay, you have the compressible Euler equations in self-similar land. Okay, do you have solutions? And I said yes. The whole first part of the talk was that yes, there are solutions. But those solutions are kind of special because they were isentropic. So S must have been a constant. Now if S is a constant, e to the S is a constant, and then this transport becomes 0. E to the S is not the 0 number, so then CF must be 0. So the implosions you guys discovered correspond to CF is equal to 0 and S is equal to 0. Cx was anyway equal to Cv plus 1, so you have only one free parameter now. Remember, we had 3 similarity exponents. One is 0, the other one is related. You have one similarity exponent. And it's 1 over lambda in the previous notation, and as I said earlier, it converges to this number. So remember, this whole story started because I said, if you could somehow make this negative, right? Now, CF is 0. This is a positive number. This is a non-negative number. So CV must be negative. And this condition is satisfied if and only if gamma, who's gamma? The power of the potential in Landau. Okay, it's not the adiabatic exponent. It's the thing you convolve with, okay? It's bigger than this number, which converges to root 3. A very, very non-physical parameter. As I said in the beginning, that the only physical parameter for Landau is -3. And now you have discovered root 3 here. Okay, fine. I mean, if we are mathematicians, we're allowed to do this. Notice, for the homogeneous problem, de Villette and Villani already proved global existence. For anything bigger than root 3 up to 2, they say, but it works up to infinity. It's not so hard. So the theorem with Bedrosian, Chen, Gualdani, G, and Yang, that we will hopefully post in a few weeks, is that you just fix a gamma bigger than root 3 in the Landau collision operator. Once you fix lambda, pick your blow-up speed, as constructed earlier with your profiles. And then you can prove there exist initial densities, which are C infinity with Gaussian decay, because that's beautiful. The momentum and energy are bounded. They in fact go to 0 at infinity, as they should. The mass density, not only is it bounded, you can put it between two constants, as you should. And the corresponding solution of Landau, you prescribe this data at time 0, and it blows up at time 1. In one sense, does it blow up? The gradient in x blows up at a specific location, x is equal to 0, for any v. But the L infinity norm remains bounded. So it's a very strange type to blow up. In self-similar coordinates, moreover, you can prove that if you take your density which solves Landau and you stick the self-similar coordinates in it, you will converge to a Maxwellian supported on the Euler implosion. So as a consequence, all the hydrodynamic fields, density, mass, energy associated to F, they all suffer implosion. Okay, I just rewrote that statement that density, mass, and energy suffer implosion, and moreover, you know the profile, okay? This is how it looks like. So F converges to a very specific function. That function, I've spelled it out here, it doesn't really matter. This is its plot. It's a very strange function. It's not like it's a radial function or something. It's a pretty strange object. Again, well, I said this earlier, that to my knowledge, it's the first example where you have a collisional kinetic model, which for homogeneous data, it's globally well posed. But now for the inhomogeneous smooth data, you have blow up. So the homogeneous and inhomogeneous problems are not the same, at least for these very hard potentials. So that's not so satisfactory. If you want to go to Landau with some actually good potentials, you better discover other implosions. And the main issue in what I said earlier is that the smooth implosions of Mel, Raphael, Rodniatsky, and Seftel were isentropic. So that parameter CF must have been 0. That's a huge constraint. So this is an issue. This is less of an issue for the proof. It's more of an issue for practitioners. Practitioners would really like to see an implosion on your computer at least. Right? Because if it's unstable, you're just never going to see it.
It's not unreasonable.
Yeah, it's not unreasonable. So you can ask now questions. Are there non-isentropic smooth implosions? Non-isentropic is very important because it allows you to decouple pressure and density. In isentropic implosions, pressure is just rho to the gamma. They do the same thing. In reality, they should do different things. Now this similarity exponent in all these implosions that I presented, you must compute numerically, and it is expensive. For Guderley, it's a shooting method. For the other implosions, it's the zeros of a complicated function. Could you just tell me an exponent and then put it on in your code in Euler, and now run Euler and see an implosion? For that, you would need stability. Otherwise, forget about it. And that's the theorem. That's the main theorem of this talk. So initially, when I gave this talk, I only wanted to start by stating this theorem and then giving its proof. But I thought then it would come out of without any enough motivation, so then maybe people didn't know why I cared about such a theorem. So the theorem with Jia Chen and Steve Shkoller is the following. Pick your favorite adiabatic exponent, maybe it's 5/3. Pick your dimension and pick an integer n. So basically we have a sequence, just like in the other results. You have a sequence of explicit similarity exponents. And by explicit, I mean I can write you a formula down. It's a closed formula. It has one strange function called square root, but that's it, nothing else. It has a square root, the formula. And for each n, there exists smooth, meaning real analytic, non-isentropic implosion profiles for density, velocity, and pressure, which are radially symmetric, and correspond to solutions that implode at time is equal to 0. I've just stated what this last sentence means. This is what it means that they implode at time is equal to 0. However, notice the strange exponents. They're different, they're complicated. Let's focus on the one for density. 2 times dimension is a positive number. A adiabatic exponent is bigger than 1, positive number, so this number is negative, okay? So density blows up at this implosion, for sure. No matter what lambda is, it's independent of lambda. The other ones for velocity and pressure depend on lambda. And you notice I didn't write lambda is bigger than 1. That's because it's not. It can be bigger than 1 or it can be less than 1, depending on what dimension an adiabatic exponent is. Now, to discover these profiles, of course you want density to be bounded from below, you don't want vacuum, but we do need to impose one condition, and that's that the pressure vanishes at the axis of symmetry, at the center. That's fine, smooth functions are allowed to vanish, but it's positive everywhere else. And the nice thing about this condition is that if you put it in the data, it's preserved by Euler. You don't need to enforce it somehow. Euler just preserves this. It's not really a compatibility condition, it's more like a boundary condition somehow. We also have stability. The strongest stability statement, of course, you're going to prove in spherical symmetry. The nth profile is stable modulo a 3 times n minus 1 dimensional condition, and it is explicit. I can write it down. And moreover, it's preserved by Euler. So you don't need to work for it. Euler just pushes it forward, this condition. In particular, the ground state is just stable. End of story. So you can put it on your computer, and Steve has done that. And yeah, it's there. Now, of course, Sergio is going to ask me, how about outside of spherical symmetry? And then it becomes interesting. We did the very detailed stability analysis for the ground state. And there are instabilities now outside of spherical symmetry, but we know exactly where they come from. So you look at this matrix.
Again, another thing is that this comes out from the Landau. They're also connected with the Landau equations.
Only when you take adiabatic exponent 5/3.
Only in that case.
Only then it's related to Landau. Otherwise it's not, because Landau in itself is a monokinetic model. There are no two species. So this is a matrix. It's called a deviatoric strain. It has this many components. You subtract one for this. And this is how many components you have in this matrix, also known as the vorticity. And each one of those entries correspond to an instability, but I call it a compatibility condition because you can just pick your data to satisfy those conditions and the solution will satisfy them automatically. You don't need to do anything.
So it's preserved by the
It's preserved by the flow. These solutions are fundamentally isentropic because while the density at the initial time is 1, let's say, at the center of the axis the pressure is 0, so you can't have a power law. And I'm nearing the end. I promised I would not go the full hour, but I still want to show you pictures. And again, pictures, you need to pick something, right? I picked 2 dimensions. I picked a monoatomic gas. In 2 dimensions, monoatomic gas is 2, not 5/3. And that's how they look like. Density, velocity, and pressure. I promised you density will blow up. I promised you, in this case, velocity will not blow up for this monoatomic gas. And the pressure is the interesting one. Okay, so here, you know, I am of a limited computational ability. The density blows up, okay? But this number is 2, and I started with 2. The pressure does not blow up. It converges to something very strange that you can write down, of course. And there are other situations in which the implosions look a bit different. And you can plot them as well. And la mulțumim, Sergio.
Yeah. Thank you.
We have plenty of time for questions.
So this profile that you mentioned at the end, do you discover them numerically,
No.
or because they are one dimension, you can just do them analytically?
Everything is analytic.
I see. So because it's one dimensional, ultimately because it's one dimension.
AI doesn't help, as Sergio said. Of course, Alex, I mean, you reduce it to an ODE. All of these things,
that's what
you reduce it to an ODE, and you just happen to solve it. Yes, of course.
So the MRRS, I guess, had lots of consequences.
Yes.
Is there anything like this that you can say here?
We have not explored this, but obviously the consequences I am interested in have to do with kinetic theory. And there are some consequences. We just don't know yet exactly what they are.
So kinetic theory in the sense of the Landau equation?
Landau or Boltzmann.
Boltzmann also? You didn't say anything about Boltzmann.
Okay, so the proof we have for Landau just is almost the same for Boltzmann, but the Boltzmann collision operator is not in divergence form, so it's a bit more annoying to work with, but it's the same. Yeah.
Can you say a bit more about the initial datum for Landau that you get?
Initial data.
For Landau, yeah.
It's it has a Gaussian tail,
But you,
and it has.
but you have to cut out the because the implosion, then the decay is not the right one, right? So
At the initial time, you have all the decay you want. In the initial data, you really have Gaussian tails, e to the minus cv squared, uniformly in x. Macroscopic quantities are all bounded. and they decay to 0 as x goes to infinity, with rates. We know the rates.
More questions?
Just a question. I'm a physicist, so I don't know too much about this thing. The pressure in the middle being 0 is very weird. You know, normally if I compress something, I expect a huge pressure in the middle. Is it because the gamma coefficients you have are not?
No, that's not a stupid question. It's a great question. Okay, so pressure in the 0 being 0 is preserved by Euler, but it's really not physical, right? Mm-hmm. Because if you add viscosity, it's going to lift it up. Mm-hmm. If you do that, this is destabilized completely. Mm-hmm. We don't know what to do. Neither does anybody. There are no known non-isentropic implosions for which both pressure and density are nowhere 0. There is no known such thing. If you discover one, it would be really nice. And because of a talk I gave in Princeton, one of the audience members told me that I should look in this old book written by Sedov, in which the claim was that all known implosions were written. I have checked. They were not.
No other questions? Yes, there is.
Regarding the very first result you discussed, is it known if the Guderley profile is stable in something?
That's a great question. So, Charles, so what?
I mean, say this is question 1.
Yes.
And question 2 is, if I take your initial data, which is a C1 1/3, let's say I regularize it even more. And you expect that sometimes it could go to Guderley profile.
Excellent questions. So here's what will happen. So in the C0 topology, you will end up green, that's a bad choice. In the C0 topology, if you perturb, so you make it a C2 here, you will be close to Guderley in C0, not in C1. And what's going to happen is out of this pre-shock, the velocity is going to carry, I don't know why I drew it like that, what are called weak singularities. I mean, you know about these. And these weak singularities are small in L infinity, but at the level of derivatives, they're not so small. And this is actually the generic picture. Guderley is really an exceptional picture. It's weird. The generic picture is that you have a strong imploding shock, and then in its wake, you have weak characteristic singularities. Like in the first talk today, we talked about contacts. So this is a weak contact, and this is a weak rarefaction. And this is the generic picture. So that's a great question.
We still have time for more questions.
Or cookies.
So if no more questions, then let's thank Vlad for a very nice talk.